Hello, my name is László Toka. I'm from Hungary, Budapest University of Technology and Economics. And this is a joint work with another Hungarian university and Ericsson Research. Well, what we did is we equipped a squash court with 2 cameras and put motion sensors into squash rackets. And then we collected the data. That's what I'm showing here on this poster. Actually, this whole project is about proof of concept IoT system with cloud control. But of course, in order to do that, we also use data science in order to do predictions, etc. So what I have here is basically a preliminary set of data results, so really basic statistics. We split the data set into professional and amateur, or I would say leisure and competitive data, and while we're comparing basic statistics of those. Thank you.
Hi, my name is Philip Myman. I'm Associate Professor of Analytics and Finance at the University of Bridgeport and also Chief Analytics Officer at Vantage Sports, where we do esports. So computers are better than humans at almost everything. At chess, at Go, at recognizing faces, at images, at human resources, at finance. Computers are better. There's no doubt about it. The one area where it seems that computers can't ever do anything right is picking a sports team, picking athletes. That is beyond the capability of all artificial intelligence, which is a shame. That you know, the Barkley quotes that you pointed out and Karl Malone, and to a lesser degree that seems to permeate through all general managers. So what I did was a bunch of machine learning algorithms to apply them historically for everything that a general manager can do: drafts, trades, and free agency. Just here I'll tell you about drafts. So over the sample period, the 10 years or so, the model outperformed the humans that actually made decisions. In almost all cases, the only case where humans did better was the #1 overall pick. The #1 overall pick, humans tend to do better than computers. Why? Any guesses? Who? If you said LeBron James, you're right. So LeBron James is in the sample from which, in the universe that humans can draw from, but not the computer because he never went to college. Dwight Howard's also in there too, but just getting rid of LeBron and keeping Dwight, still the model would have done better. Is there another? Oh yeah, thank you. So overall, how did people do? If you translate this into wins and translate wins into dollars, then teams did really poorly. For example, Minnesota lost out on about $300 million of on-court productivity that they could have had over the 10-year period. That's about 69% of their franchise value. That's very unfortunate. On average, the teams lost out on about $130 million, or about a quarter of their franchise value, if they had just drafted according to more automated approach. Now, does this mean that we shouldn't have any human general managers at all? No, we still have human chess masters. We have human Go players. We have human resources people. We have human people in finance. But in all those domains, it's understood that computers are better. And we use computers as a tool. There's no give and take. We've lost. It's over. We should apply the same thinking to sports and start using these approaches as automated approaches as tools. So I've put all of these tools online for free, available to anybody at nbagm.pm. Thanks.
Hello, so my name is Stefan Zhang. I'm a PhD student at Caltech. And our poster here is about sort of moving a little step towards like developing a full AI for basketball, which is like a really hard multi-agent game. It's adversarial. There's all sorts of like rich spatial temporal dynamics going on in this game. And so in particular, this poses a really, really hard situation if you wanted to develop a general AI agent that could maybe one day beat basketball. And so one particular aspect that we focus on is the question that when you have really high resolution spatial temporal data from basketball tracking of professional basketball players, how can you sort of learn strategic behavior that involves long-term planning from this data? And the problem really here is that if you're a human player, you really behave, your behavior can be sort of thought of in sort of the short term and the long term. Namely, the short term is like sort of the behavior of your muscles, but the long term is sort of what your brain wants to implement as a plan over like the span of a few seconds. And so this is something that's really hard to learn. Using every current technique that we have, this is still something that poses a significant barrier to really understanding what a general AI would do when it plays basketball. So our approach here is to use a hierarchical deep neural network. It reasons on multiple timescales, and we showed that by training it on a large data set of these professional basketball player tracks, we can predict long-term goals and instantaneous movements simultaneously in this neural network. So on the left, you see a picture of data that we have. The green track is a basketball player, the orange is the ball. And so we let this neural network look at these pictures, and then we show that it generates fairly realistic player movement. That we see that the model sort of captures long-term intent. And we show that we did a user study with professional sports analysts, and we show that actually most interestingly, I think, is that the tracks that we produce with our model are on par or competitive with ground truth. So in a very limited setting, we can sort of say that we've almost passed the Turing test for generating realistic basketball behavior. So come and chat, I would say.
So my name is Jan van Eyre. I'm presenting joint work with Siba Handelset and Jesse Davis on strategy discovery in professional soccer metadata. More specifically, the task we addressed in our work is defined as follows. Given a set of matches where each match is represented as a sequence of events, possibly enriched with player and ball tracking data, find relevant spatio-temporal patterns that characterize attacking strategies. So to address this task, we have developed a four-step approach. In the first step, our approach covers relevant phases from these event sequences, where a phase is considered relevant if it results in a goal attempt. In the second step, our approach clusters together phases that are spatially similar. In the third step, it mines frequent sequential patterns from these clusters and ranks them according to their interestingness. And then in the fourth and final step, it presents the top-ranked patterns to the users. So in the bottom right corner of the slide, there's an example of a pattern discovered by our approach. So if you want to find out more about this work, then please come talk to me during the poster session or during the Applied Data Science poster session tomorrow night, where I'll be presenting a poster on strategy discovery in volleyball.
Hi, I'm Mason Wright. I'm a PhD student at University of Michigan in Ann Arbor, and this is joint work with Jenna Weens, who's one of the organizers here. She's a professor there. Our work is called Method to Their March Madness, and it's basically an exploratory analysis of a large data set we collected of pool brackets from the 2015 and 2016 NCAA men's basketball tournament. And what we eventually hope to do is predict the distribution of entries for a future tournament based on features of that tournament, such as estimated win probabilities between all pairs of teams, team IDs, and so on. And this could allow us to derive a best response to the predicted brackets of other entrants in a given size of pool. And so what we present today is just exploratory. So we have about 200,000 of these brackets, and we can show the expected score based on estimated win probabilities between the teams, plot that against the actual score, for example, like you see here. And we can observe things like, for example, 2 and 3 seeds tend to be underbacked to win the championship, in that you might get a higher expected value if you pick someone who's nearly the most likely to win, but not a 1 seed. And if you want to know more, just come by the poster.
Hi, I'm Burt Monroe. I'm a professor of political science at Penn State. I direct our new PhD program in social data analytics, and my senior authors are 2 PhD students at Penn State, Christopher Boyle and Ryan McMahon. Since 2008, the NFL has posted on its website about the combine scouting reports about the prospects. We took those scouting reports for the 175 quarterback prospects and looked for words, language that differentiated white prospects from non-white prospects. There's more detail on the poster, but some of the things that stand out are character, intelligence, mental characteristics are more associated with white, language used about white quarterbacks, and physical characteristics are more associated with non-white quarterbacks. In fact, the actual weight of the prospect is not as predictive of the use of the word weight as the race of the quarterback prospect is. The sociology literature also predicts other types of stereotypes that will be used that are more subtle. An example down near the bottom is that non-whites will be described as not responsible for their own success or their own failure and be set upon by external forces and that sort of thing. And we found that as well. We also find the languages, the grid has disappeared. It's over there and on the poster. Can be used to help predict draft position, but in some counterintuitive ways. In particular, things like language about leadership, consistency, intelligence is rarely used about non-white quarterback prospects, but when it is, it predicts much improved draft position, much more than it does for white quarterbacks. And there's some opposites in type going, in language being used against type for whites as well. Thank you.
All right, let's thank the Spotlight presenters again.